So hello, I hope you can hear me fine. My name is Matthias from Novatech, and this is going to be my talk about building container images. So I'm going to start sharing my screen real quick. All right, so I hope you can all see that presentation now. And I only have like about 30 plus few minutes and quite a bit of ground to cover. So I'm going to try to make the intro fairly short. So welcome to the ContainerDays. Hope you're having all a good time. What I'm going to talk about today is primarily described in that scenario. I think probably most developers among us will know. Basically the various ways or the options how to get your code into a container image. So you probably heard about containers. It's a pretty popular thing at the moment. They even have conferences like these ContainerDays. So we might give this thing a closer look on what kind of options are around to build those images. So we're going to talk a little bit about Docker, the evolution of Dockerfiles, and then look at other things like chip and Cloud-Native Buildpacks. And also have a look on other options. I just don't have the option to demo everything live within 30 minutes. So a bit of an intro there for people new to the topic. Let's kind of go quickly over what actually is a container image, or even start a step earlier, what is a container. I'm going to fast forward through this because I'm pretty sure you mostly have heard about that. So in the end, a container, or the idea of a container, is to have a separated, or even better, isolated process or application that brings along all the processes, the process libraries, dependencies, and to be like a full self-sufficient component that can pretty much run everywhere and brings along all its stuff. So it's kind of separated from a shared operating system kernel by various system calls. Now, those system calls are kind of complex and difficult to use. So most of you will probably have heard about that thing called Docker, which is like a one container daemon, a pretty popular one. And this one, as well as others, will provide an API that you don't have to do all those system calls and can run a container with a pretty clean API. Now, as we know what containers are, like those container images are basically templates to run those containers. So they are, while a template is not just like a blueprint, so to say, it's something that resides on your file system, whereas once it's running, it's like a running process that uses all that and runs it on this so-called container daemon. Now, those images are the point of focus for today, and to give a bit of history and about a few internal details, you might have heard that those images are not coming as a big blob kind of storage artifact. So they're separated into layers. And in the very beginning, it was like that an image was, we saw that before, was changed into a running container by calling run. Then you could do some modifications on that image, on that container, and commit it into a new image. So those images are always immutable, while the containers are the thing that you can work with. So you would run a new one. And in this case, you would build a container that brings along a base image, a Java runtime, and a Java application, which would result kind of, as it described here, in the three-layered image that you can distribute all over the world, and everybody can run it without the need to install Java or anything else. They just need to run that container. Now, Docker very soon came to the realization that this approach might be a bit too awkward. And Docker came out in, I think, March 2013. So this was May 2013 when they first mentioned the term Dockerfile in the history. So this Dockerfile is kind of a batch script that runs and builds the individual layers of your container. As you can see here again, we're getting a base image, we're installing Java, we're copying our Java application, and then we tell basically Docker, so this is the command to run this run this Java application and using all that stack. And now things evolved. There were more and more images on that marketplace, which is called Docker Hub. So you could have like an OpenJDK image like this, or an OpenJDK image like that. And in the end, you would get quite a few options as opposed to building the image yourself, which is also an option, which could lead to the confusion. Like it happened, a developer from our company came to me and said, like, so you work with containers a lot. What is like the best Java container base image? And I was like, I don't know. I mean, I'm a consultant. I would say it depends, right? It depends on your application. It depends on who owns it. It depends on who calls it and so on. So give you a bit more background. Now, I also asked, how do you use that? I mean, how do people use that container image? So why do they use it? I mean, in the end, as I said before, the containerization step is a standardization step. So you build something with a predefined abstraction that pretty much everyone can use in the same way then. So very often, I mean, this is a Java example, but this is just as true for all the other programming languages. You would get your code or runnable artifact into such a container, and then it's distributable. You can run it on a development workstations, you can run it on Kubernetes environments, and so on. So that standardization step happens running that Docker file and building that container. Now, building the code is also a step that people would want to have standardized, and not everybody do it on their own. So basically, people would probably execute those steps in certain pipelines. But if you could extend that scope of the Docker file to this, it might be a helpful thing. This is also, and doing that in case of Java would probably look like that. So to get a based container, installing the build tools, copying the source, building the source, then removing the build tools again, because you want to have that image as small as possible, and install the runtime and configure everything. So that could be a fairly like cumbersome Docker file. And Docker also saw that need and came up with something which is called the multi-stage Docker file. So in this case, it's basically still one file, but you have separate so-called stages. So in this would be like the build stage, and this would be like the run stage, so to say. So in this case, I'm taking it's like a Java example, taking a Maven, which is like a build engine for a Java container, and then copying the source code in and building that source code into a final jar file, which is basically the packed version of a Java executable. And then this container basically is done. So we're creating a new one here. And in this one, we're just taking a base image, as we saw before, and copying that jar file from the first step into the second step. So what we achieve with this is that we can basically distribute that file and know that everybody who runs that file will use this container, build the code in exactly those steps within a container, and then build a new container to run it. So also we can guarantee that this is a more standardized way, as opposed to developer building the machine, building the code on various developer machines, which might lead to certain differences there. All right. So the development of Dockerfiles didn't come to an end at that point. In 2018, they started to adopt technology called BuildKit to change, to improve on various ends, like better, bigger, faster, more, whatsoever. I mean, bigger not in the terms of Dockerfiles, bigger is smaller here. So you want to have them small, you want to have them fast, secure, good caching, and so on. So what they also added was like parallel stages and flow logic. So based on that concept of stages, you could now, if you have multiple of those, say, if they don't depend on each other, you could run them in parallel, or like Docker would detect that they can run it in parallel. So you'd save some time. And then also put some flow logic in, like if this one went well, then do this one, or the other way around, and so on. However, it also kind of led to a way that you can take things to add an unnecessary complexity here on a Dockerfile level. Anyway, there was a few good things that came along. So for example, you could add own customized front-end images that might change the behavior. So example for this one is like you could mount a cache in a Docker file. So this is basically possible for a Docker container, but it wasn't possible in a Docker file until then. So whenever you build an application with like NPM or Maven, you will know that those steps to take such a build step take a long time, because without a cache, they would just download all the libraries over and over again. And with that, they could like access something on the out of file system outside of the container daemon, store the libraries there, and then reuse them in a later step. So while this is not 100% repetitive, so to say, because you reuse something, that still might improve quite a bit on your build step, especially within development. So it's possible, but handle with care. Now, if we look back at like the development of the Dockerfiles, we could say what were the criteria which makes a container image build great or makes a container image great? So it's like, yeah, run it, if you build it fast, run it fast, have it small, have it well structured, have it enable a high degree of standardization, make it secure, security is missing here, and so on. So taking a step back, especially on the topics of size, speed, and structure. Now we've seen those images come in layers. So if you do like a run of that image, it will download all the layers in the first run. If you repeat that, it won't download the layers again because it already has them cached. So optimizing on those bottom layers might not make too much sense because they normally don't change very much. What will probably change a lot if you rebuild your images is like the application layer, because that's where new code goes in. So it might make more sense to optimize on those things that change frequently rather than on the ones that change rarely. And we will see approaches that do that. So talking about those approaches, we've seen Docker, the various options of Docker. And then there are other things. So even before Docker was released, there were things called Buildpacks that was used in Heroku and Cloud Foundry. There were things like Maven plugins where you could get out a container out of a Maven or Gradle build. There was things like Chip and Podman and others. But one term that goes for that a lot is like the term Buildpacks. By the way, I need to give credits to that image. This was done by in an excellent blog post from Jonas Hecht from CodeCentric. So beautifully done. I really like that. And now we're going to have a look at this Chip and Buildpack thing. So Chip, as the name implies, is focused on Java applications. This is, of course, a strong limitation as opposed to Dockerfiles, where you can like do everything and all kinds of languages and frameworks. With Chip, it's like limited to Java, but it brings in along some interesting aspects. So if you have your Java source, and in the previous versions, we always had to build the Java source before we had to like put it into an image or do the build step within the image. Now with Chip, you run your Maven or Gradle to build the jar file. And out of that comes not just a jar file, but a containerized jar file. And you run that either in your pipeline or in your local OS or wherever you have like your Maven stuff installed. You can even do that in a container, of course. Now, the interesting thing is what you don't see on that picture. What you don't see on that picture is like a Docker daemon. So if you do run a Docker file, you need a Docker daemon to build that for you. Now with Chip, you don't need that. It will create the Docker file, the Docker container or the container image. It's not like per se a Docker image, it's like an OCI compliant image out of your Maven run. And it doesn't need the Docker file to do that. So it could directly push it to like a Docker hub. It could build it to a local Docker daemon. I said it doesn't need it, but it can put it in there, or you can just export it as a tar file. So this is all pretty cool, especially if you want to work in pipelines where sometimes you might have the limitation that you can't run a Docker daemon on a build node or so. This will come in very handy. Now we talked about before about those changing layers and dependencies and so on. Now Chip also takes this forward and says, in the case of Java, we don't see the application layer as one big application layer. We know that this has also kind of sub layers. So there are dependencies, there are resource files, and the class files. So this concept goes on to here, where you all can say, basically what changes often are those class files. Even those dependencies might not change so much. So basically chip splits up that top layer into 3 like smaller layers. And very often only this one will change. So your new image will only be a few kilobytes, and that can then improve the loading and starting time quite a bit. So this is the overall for that. Now, let's look at Buildpacks. The general idea of Buildpacks comes out of the initial version of platform as a service. Like Heroku was probably the first PaaS public offering with the idea. So like you give us your application code and we run that for you. And in order to do that, they also came up with like a 12-factor kind of idea to say, to do that right, make your applications in a 12-factor style, and we can do all the scaling and cool things with it. But the first step was always to like have the code runnable at some stage. So the Buildpack idea was like to detect what kind of code is it? Is it like Go, Ruby, Python, whatsoever? And then find a way to build that and turn it into a runnable artifact that could be run on that platform. Now, this idea was so good that Cloud Foundry adopted that. So the Buildpack development continued in both PaaS versions. And then with the rise of Kubernetes and Docker and their big popularity, there was an idea to say, well, why can we use this concept only within the platform? Why can't we use it externally, as people are so crazy about building containers? Then the CNCF adopted this Cloud-Native Buildpacks thing as like a new project. And this was meant to be like a reference implementation or a definition of that. So you could do your own Cloud-Native Buildpacks implementations yourself, following that guideline, and then you could use that API. One of that implementation is Paketo, which comes out directly of the Cloud Foundry Foundation. So it reuses the Cloud Foundry concepts, the experience, and also, of course, the robustness of the Buildpacks that have been there for a while, and as an external implementation for this specification. So how that works is, like, first thing I can say is you need a daemon here, a container daemon, because if you run that API with a command called pack, it will download a so-called build image. So within that image, it would contain all the mechanisms to detect this code, to find according Buildpacks, to use those Buildpacks and come out with an application image. And then have those layers in that final image according to those Buildpacks. So this is very generic. It's totally independent of like a certain programming language or framework. And it has another feature in that you couldn't see in the first place. So now that I told you the top layers will change very often, this one has also a mechanism just to exchange base layers. So what that means is, for example, there might also be this situation where you don't update your code, but you might have to update your base image because there is suddenly a detection of a vulnerability or some security breach or whatsoever in the base image you used. Then with the Buildpacks, which basically provide the base image anyway, they have a rebase function to just exchange that layer and transform it in a new image without changing that. So this can be done in a very fast and efficient way. Now, looking at Paketo as a real-world implementation of that, it comes with a couple of predefined Buildpacks for various runtimes. So we got .NET, PHP, Node, Go, Ruby, some Java, and also GraalVM on the Java side. And now this concept might start to make more sense to you, because if you think that each developer each development team can bring their own image and their own Dockerfile, it's very unlikely that they come all along with the same base image. So as you've seen with the Java, there's some pre-built base images, and might be the case for other frameworks as well. So in case you have that vulnerability detection, the first thing you need to do is figure out where am I affected and where am I not. Now with this one, if you use Buildpacks across the board for all your builds, then you will know all of my container images will have the same base image. And then you also know, okay, am I affected or am I not? And if I'm not, I don't have to do anything. If I am, I have to rebase everything. And this was a concept which was applied in Cloud Foundry internally. So there was only one base OS for all of the applications, which made it super easy to patch something in case there was a threat. And this was the idea to outsource here to standalone containers as well. Now the flow for Paketo is exactly the same. Here again on an example with the Java file. So you run pack, it downloads the thing, and it will detect, so there's a Java application, and use the according layers and build that. And in here you would be able to see, well, the same thing as we saw with chip before. You have like a base OS runtime and everything, but it also detects on the Java side that it can optimize and separate on these layers here. If you happen to have not only a Java, but a Spring Boot application, you could even use this mechanism in your Maven and Gradle builds. So you just like do like a Maven Spring Boot build image, like kind of command. I don't know at the top of my head, you'll see it in the demo. And then you would get that jar file packaged, like split it accordingly, packaged in a container, and you can apply it this way as well. All right, so coming back, so what's the best Java-based container? There's no clear answer. It's really about who do you want to, like, who has the ownership of that, and especially of the base layer. So does your company provide something where you have like a maintained image repo for base images? Then you can easily use Dockerfiles and use those. And also, who owns the build process? Who will be called if things go wrong? And so with the various options you have seen, it's basically your choice who you're going to trust and who you want to outsource the responsibilities to. So I'm not saying one is better or one is worse. They just all have different advantages and things to consider when you put them in a pipeline. Now, let me see what the time says. So we got about 10 minutes left, which isn't all the way bad. I have prepared a repo with an example code. I'm going to share that with you later, with various Docker files. So it's like a simple application. And I have like a kind of a walkthrough here as an ASCII doc, so you can try the various things yourself, because I might not get everything into the demo today. And here we have those various Docker files. Now I'm going to jump in here real quick and say, well, let's do like first plain one using that adopt open JDK. So the command to build a container is like docker build, and just see if I have that in my history. Yeah, I'm using that one. So I'm building a container called Java app version simple adopt open JDK. So what's going to happen now? It's going to send the pre-built jar file to the Docker daemon. Docker will download the base container and then run through that steps. So it's first step, second step, third step, and done. So if we look at that images, we can now see this one was just built right now. If we inspect or do like a history of that image, how this all came together. So this is the first one. I can use just the first 3 characters here, E8A. Then you will see there is some base layer here. So most likely this was the operating system base layer. This or that, this was like an update of the OS image, then installation of Java with 128 megs. And here with 19, we have that copy file. This is where we put in our Java application in one big step. Now, if we want that multi-stage thing and build the code ourselves, so I'm using that multi-stage builder now. And as you can see, it has to download this Maven image in the first place. A couple of that is already there. And then it's going to run the Maven command. And what's going to happen now? Now it's going to download all that necessary dependencies. And whenever I do a change in my code, this step has basically to be repeated. So whenever this is done, in the next one, we're going to look at this experimental one where I commented this line out and just added this mount point here. So this one's still running. I hope it's not going to take too long and to ruin my demo. So if this happens in the pipeline overnight, it's not a big drama. If this happens through a live demo very short on time, it's not the most pleasant thing for the presenter, but it's real world, right? So we're now already in the last phase. So anyway, sharing that Docker file will basically mean that everybody who wants to do that will do it in exactly the same style. They will download the same libraries, they will be checked, and the image that comes out of that will always be the same. So if I look at the images now, I have this one with a multi-stage build. It's pretty much exactly the same size. What a surprise. But the build was completely different. And you can also see this none image here. So this was basically the first step, the first stage, basically the download of this Maven part. And this is a lot bigger, but that doesn't care. That doesn't matter for us because we're not going to use that later on anyway. So this will just be thrown away at some stage. Now, if we want to run that multi-stage build with the cache, this one, this one's going to complain because we need build kit enabled. So this is the new style for Docker then, and now we can run it like this. So also, if you run it the first time, this might take a bit to run through all the Maven stuff. So we might have to wait here a little again. So it's now coming to the point where it says, okay, clean package. So this might take another minute or so. In the meantime, I want to just change the code real quick. So I want to go sure if you run it again, that it has no option to cache something here, and can continue with previous settings. So we're at 30 seconds now. Looking at the time again, yeah, it should be all right. So this should again end up in a time frame of about a minute or so. So yeah, the download thing won't be quicker. This depends on my local landline here, which might not be the very fastest. Okay, come on, hurry up. All right, so this is done in about a minute. So if I repeat that now, it will probably figure out that I have done all of that before, and it just stops, right? So it doesn't rebuild. It knows that. But now if I say, okay, I'm going to change some code like that and rerun it now, so it will detect that it's a new build. And this happens right here. But now it doesn't download all the libraries. So it uses that cache and is totally happy with this. So the build will be significantly faster. So it's not down to 12 seconds or so. So that's quite a help. And no, not Docker history, Docker images. You can see we're getting more and more images, and we get a lot of these none images because they're going to be dropped anyway. And they're all very similar in size. Now looking at this component called chip, with this one, I'm building to my local Docker daemon and calling my application java app.chip. And so this one will scan the project as well. This, of course, can use the local Maven cache. And as you can see, this one is really super fast as well. So after 12 seconds, the build is complete. And if you look in the images now, you won't find it here on top. You will find it on the very bottom. It says here like chip, and it says like 51 years old. So why is that? The point is, if you rebuild a Docker image, the image state also always goes into the ID. That means you potentially have different IDs for two totally complete identical builds. This one is something that Chip and the build packs don't do. They say, well, they take a very static date from very far in the past and use that all the time. So they can recognize if a build is totally equivalent and just use the same image ID and provide more consistency there. So if I inspect this image, which I just built now, it's 86C. No, I didn't want to inspect that. I wanted to do a history. Well, the inspect would probably give me the details as well. And now you can see I've changed, this has changed into like classes, resources, and dependencies. If we go back to the images and even take the last one that I built with the cache and build kit, we still have the point that one big copy step brings in all of the application, as opposed to using Chip, where this has been split up and we can see like 18.9 of the 19 megabytes is all dependencies. So the part which really changes in a rebuild is only that. And that can be done pretty quickly then. All right, so finally I wanted to show the pack part. So I'm executing it right out of here. So and as you can see, I specify nothing. I just say a pack build and provide a name. And then it will say it's downloading that builder image, which I already have. So it's not downloading it again. And then it detects the application and it finds out, so this is a Spring Boot Java application. It needs a Java runtime, a Tomcat, and so on. So all of those build packs are matches, and those build packs will then be used. And then it goes through all those steps. It detects it's Java 11. I have some cached layers here because I had built it before, but it also rebuilds something in case it needs it. So you get all this beautiful output here. And if I do the Docker images now again, I have this one, which I have just built. And if I do a Docker history here, which is the 545, then I can, well, I don't get much information out here. I can tell you that, however, that here on the top is those kilobyte kind of things, either this one or that one, are the class files. The 18.9, that's again the dependency jars. So this is using the concept as well. You can see that also in the log output that it slices those layers into dependencies, Spring Boot loader, snapshot dependencies, and application. So this one works in the same way, just in this case for Java. Now, this is pretty much what I wanted to show. The only option which is still left over is to show you that with the Spring Boot Maven plugin. So if you run that, then it will also do your local Maven build. But after that, it's taking the jar file and it will then figure out, okay, this is Java 11. I needed the JRE 11, so it's going to download that in case it hasn't had that cached, and builds the image according to that. So if I would now come in and say I want a different version of my application, so I'm going to my POM file and say now I want Java 16, which on the Docker side would mean I have to rebuild all the images. And change the Docker file and change the base image, find a new Java 16 base image, and so on, and restart the process. Whereas here, I just run the same command and let the build packs work this out for me. So they will probably see in a second after they have compiled that the new version is now based on Java 16. So Spring has already detected that. You can see that here. And now the build packs have detected it as well. So my application stack in the container image is updated just by the mechanisms they have in there. So we won't watch it to the end. I really want to finish this one up. First of all, say thank you for listening. That's me. That was what I looked like before COVID times when the hairdressers were still open. If you want to play through that, what I have just done, feel free to scan this code. It will link you to my GitHub profile and to that repo, so you can play along with that. And this is all I wanted to share for today. So thanks very much for listening, and hope to see you all in person soon again. Thanks very much.